Hello and welcome to session 2 of the 2025 Uncrewed Systems Virtual Conference, leveraging secure AI and sensor processing at the edge on autonomous platforms. My name is John McHale, EVP and Group Editorial Director with Military Embedded Systems, the SOSA Special Edition, and the FACE Special Edition. I'm also moderator for today's event. To learn more about Military Embedded Systems, please visit militaryembedded.com and check out our articles, blogs, and podcasts on military technology. Our speakers for this session are Cale Stevens, VP Advanced Technology at Crystal Group, and Matthew Fahrenkrug, Senior Embedded Software Engineer for Star Lab. The session is sponsored by Crystal Group and Star Lab, and the overall event is hosted by Military Embedded Systems Online and Open Systems Media. Now, before we begin, I have some housekeeping items. This and all Open Systems Media virtual events are copyrighted and may not be recorded or used in any way without the express and written consent of Open Systems Media. This session will consume about 40 to 45 minutes, leaving the remaining time for the Q&A session. Now let's take a quick look around your viewing console. You'll find on the right-hand side an area where you can enter your questions in real time. We're encouraging you to ask questions throughout the session while the question is still fresh in your mind, and we'll address as many as we can during the Q&A portion. If you have a question for a specific speaker, please note so at the beginning of your question, or I'll offer it to all of our speakers. If you have a question pertaining to the event operation of itself, one of our technicians will get back to you during the session. Please note that as much as we'd like to, we may not get to all of your questions today. In that case, someone may get back to you after the event with more information. On the other side of your screen, you'll see the resources section. And that's where you can find the slides being presented today, and below that, you'll see speaker information. I've got two more console features to share. Your console is customizable insofar as you're able to manipulate all of these widgets, Q&A, resources, and presenters for your ideal viewing experience. You expand them to get a closer look or close them to have the presentation window automatically resize around them. For maximum screen size, you can close them all or use the full screen control in the upper right-hand corner of the presentation window. To bring them back, simply click on the buttons in the bottom middle dock. We also have closed captioning capabilities in nearly a dozen languages. To enable this functionality, click on CC in the upper right-hand corner of the presentation window and select your language of choice from the drop-down menu. This session and event will be archived online at the same URL you used to join today's live session and be available within 48 hours. Once up, it'll be available for at least 1 year. And now let's get it started. Cale, take it away.
Awesome. Thanks, John. Howdy, everybody. We're going to spend about 15 or 20 minutes talking about what's probably a topic that should take about 6 or 7 hours. So just going into this, expect that we're going to be hitting this at a 10,000 foot altitude. Happy to talk more in the Q&A and afterwards. So what we're going to talk about are three considerations for bringing AI to the edge. And those three areas are ruggedization, security, and speed. And we'll drill down into each of those here in the next 15 or 20 minutes. Just so you know who's talking here, my name is Cale Stevens, VP of Engineering and Advanced Technology at Crystal Group in Hiawatha, Iowa. Crystal Group does ruggedized compute, storage, and networking solutions for commercial and defense customers and applications. So think boat, ships, tanks, fighter bombers, trainers, industrial applications, that kind of thing. I've got about 25 years of experience in aerospace and defense, working both commercial and military programs. When you think commercial, think your air transport airplanes, business jets, as well as lots of fighters, surface vehicles on the ground, undersea, that kind of thing. And I've had the privilege of working around the world with end customers and acquisition authorities and everything in between, with small boxes all the way to system of systems. Did a lot of work in bringing a lot of big compute to the edge, which is kind of what AI at the edge is all about. All right, so bottom line up front here is that when we talk about bringing AI edge solutions to kind of reality, the customers, the suppliers, the engineers, the business, it ends up being this process of balancing three broad categories of capabilities: speed, security, and ruggedization. In an ideal state, you know, maximize the speed, you got perfect security, and you've got ruggedization, with margin and all that to spare. The reality is you're going to have to balance these things and find that sweet spot that creates the sufficient speed with all the security and the ruggedization, the thermals, the vibe, and everything that enable the mission, the customer, whatever it is, to actually do what they need to go do. So over the next several slides, we'll drill into speed, security, and ruggedization. All right, let's start with speed. So when we say speed, think processing, general purpose processing, graphics processing, memory, sometimes mass storage, depending on the application and the underlying interfaces. And what's happening, at least with AI, is you've got a lot of end systems, edge systems, so autonomous vehicles. I don't care if it's ground, air, it doesn't matter. But you got a lot of data that's coming in, whether it's in sensors, over data links, it's big databases, and they're processing that information. They're, inference engines or whatever it is. And so what you've got is a lot of technology, a lot of data, and very time sensitive type stuff. Grab a frame, analyze it, output, next frame, process, output, and so on. And that environment, frankly, is changing. To say it's changing quickly is, well, it's cliche, but it's true. And so what you end up dealing with is accepting the fact that you're going to get more and more data over, 1/4, half a year, whatever it is. And so you've got to be able to scale and modify and change and respond to more sensors, higher resolution sensors, more data. You also have to kind of get your head around the fact that you're going to be dealing with kind of a server class, general processing, graphics processing compute solution. So think the guys that are the data centers that are running all the AI for ChatGPT, Copilot, Gemini, Anthropic's Claude, and all that good stuff. So that's kind of the mindset you have to have around what do you need for a compute architecture. Additionally, that conversation kind of shifts your preference, if you will, or over to, well, you're probably going to have to go do CODs. Why? You want to leverage all the goodness that the industry is pushing into the processing, the storage, the memory, the motherboards, and perhaps you can develop yourself at cost, sure, or you can leverage all of the good things that those suppliers are already putting into their technology. So think server class, lots of processing capabilities, moving quickly. If there's anything that's going to be a challenge, it's thermal management. So when you're talking speed, you should equate speed and thermal management. And everybody's familiar, hopefully, with Moore's law, which says that compute doubles about every 2 years. Well, for the software engineers in the room, you have Great Moore's law compensator, which is essentially you're going to consume all of that processing capacity the moment it becomes available, if not 1 millisecond before then. AI at the edge is no different. It drives significant processing power requirements in what is ultimately generally a very dense or a small form factor. So where you got to get the power to the processor, sure, that's a challenge for sure. What's the bigger challenge is going to be removing the heat, removing the thermal. That's the bigger challenge here. And so when you're going into these projects, what you need to do is think about what's the decision-making framework, the trade space that the customer, the suppliers, the integrators, the designers, what is that decision-making framework for them to have and be able to trade size, weight, power, cost, speed capabilities, processing capabilities, memory capabilities, because ultimately you're going to have to figure out how do you balance between the speed and what's probably going to be your primary limiter, which is thermal. All right, so enough about speed. And by the way, again, that's like 6 hours in 4 minutes. Next up, let's talk security. So security is, I think security is like a multi-year, multi-generational kind of conversation. But when you think security, think about whether you're dealing with things like your data at rest, so what you're storing, or your data in transit. Whether you're doing your traditional type 1 encryption, which is a lot of times for tactical data links. The NSA's got a really great approach to using commercial solutions for classified, or CSFC, that's in the upper left. And so you got to think and be very clear and aligned with the customers, the users, and the designers of what are we putting security on and what type of security are we talking about? Because that will ultimately drive significant impacts into the speed, because anytime you have encryption, you generally are going to take a hit in bandwidth and processor capacity, or basically you're going to erode some of your processor capacity. Additionally, you got to find room for this stuff, whether it's logical if you have software, whether it's hardware if you're using like a type 1 encryption unit, for example. 2 other areas to consider when you're thinking security is, it's been around for a while, but it's really increasing in terms of the scrutiny in the last couple of years, is supply chain integrity. So that's things like ensuring that the parts that you're getting from supplier A is actually what they designed it for, and that nowhere along the supply chain has anyone introduced any nefarious devices or software, whether it's BIOS, BMC, sometimes they add devices, that kind of thing. So you got to figure out the supply chain process, your checks, and your whole integrity process for that. Last thing we'll talk about, and I've got a slide on this because it's often overlooked, is okay, what about exploitation deterrence, which is a fancy way of saying anti-tamper or tamper detection or something like that. So if we go to that, what we're talking about with exploitation deterrence or tamper detection or anti-tamper is essentially how do you detect and what do you do when you get unauthorized access into your box? Okay, and the way you approach this, there's a lot of if you're bored and you got a couple of days, go out and you can read a bunch of NSA documents and whatnot about what it is. But essentially, what you got to do first is define what that security boundary is. That's the area. That's the volume, literally the box that you're going to say, this is my boundary that I'm responsible for creating the security boundary for. Then what you need to do is, okay, for that within everything within that boundary, it's within a particular environment. And when I say environment, think like it's sitting in a lab or it's on a side by side over in the desert. And what kind of capabilities, functions, technical things do you need in that box to detect tampers? And I mentioned here in the slide false positive. For example, you can have vibration sensors in your box. You probably don't want those on an autonomous vehicle because as soon as you hit a bump and it detects a tamper event, it zeroizes, sanitizes your box, and now you got a brick. The last thing you're going to want to go consider is whether you need remote control, whether that's remote notification or actually the ability to sanitize and zeroize from remote. All of those things you take into account, you trade the design options, ensure that you've got some alternatives. The response to that the response to the tamper event is going to end up driving a lot of design, whether it's in software or hardware, a lot of design implications. So it's things like, are you going to sanitize, zeroize? How quickly are you going to do that? And what certifications or accreditations are you going to need? There are some devices, kind of self-contained devices out there that can help simplify this. For what it's worth, Crystal Group has one called Tamper and Zeroization Response Device, and its focus is on essentially having a self-contained, basically tamper detection, zeroization, and sanitization function. You can use it for data at rest or data in transit. And you're looking at, okay, how can we have a self-contained sort of AT, anti-tamper or tamper detection thing that is also survivable in those rugged environments? All right, speaking of rugged environments, we come to after we come to the last section on this, and then I'm going to get into a quick use case. So after you figured out all the processing and after you figured out all the security, now you got to go ruggedize this. And while this may be pretty obvious to y'all, this is where the challenge really is. This is where the constraints really end up being. When you're thinking in ruggedization or environment, think about what really is the shock and the vibe that you're going to have to experience. Think about the environment in terms of, is it dust, is it sand, salt, fog, EMI, EMC. Be thinking about your temperatures, whether you're storage, cold storage, hot storage, operational, short-term operational, that kind of thing. And you're going to want to make sure that we're talking about this not at the vehicle level. This is what's happening. That's important and something that we want to make sure we understand. But more importantly and what is the environment around the box? Because you could get into a situation, particularly around shock and vibe, where you're over designing because your box is actually well isolated within like a ground vehicle, for example, or you're under designing because somebody said, oh, there's no vibration, but you happen to be sitting on top of like a howitzer. Either one of those, you need to make sure you understand what that environment is. Ultimately, what you're endeavoring to do is ruggedize the equipment for three things: durability, reliability, and availability. All right, so ruggedization, speed, and security. Those are the three factors that you're going to take into account when trying to bring AI to the edge. I got a quick case study here just to kind of demonstrate sort of some of the trades and balances and optimizations and approach you should consider when doing AI at the edge. And what this one is around an autonomous vehicle. Think of a side-by-side in a sandbox or in the Arctic, whatever it is. So in this particular case, we're going to go do something in the desert. So you're going to have maybe a -30 to +55 C temperature range, plenty of things to get inside the box and cause terrible disruption. Dust, salt fog, fluids. If you're talking autonomous ground vehicle, you should assume it's going to get wet. A lot of vibe, as an example, 12G RMS. Power on this guy is something to consider. A lot of vehicles are going to be DC voltage, maybe 18 to 36, but that doesn't mean, get on airplanes, you get some 400 hertz stuff, 220, all kinds of stuff. And then this is where, your customer is going to say, hey, my particular system requires roughly, let's say 2.5 gigahertz of 64 core processing, and I need two 600 watt GPUs. Okay, so what we got is we got the environment, roughly, we got the shock and vibe, we know our power, then we know roughly our processing capabilities. So what does that mean? Well, you go for speed, yeah, it makes sense, but remember I talked about thermal. So I know that the the central processor is at 280 watts, the GPUs end up being about 600 watts each. I'm immediately at 1500 watts, and I haven't even actually done anything, right? So add some memory, add some storage, and realistically, you're looking at 1800 watts, maybe plan for 2000 watts within a box. Add the security. So on this one, maybe it's CSFC for both data at rest and in transit, which means I gotta use a little bit of that processor for some of the CSFC processing. Plus, I need to make sure I have the hardware hooks in the motherboard and the CPU and the GPU. And then based on the environmentals that we're talking about, I would love to say, hey, it's a sheet metal chassis, all open, no big deal. We'll put a couple of filters and it's fine. That's not really realistic. When you're talking about, 2000 watts at these kind of temps, you're probably talking about, and this kind of environment, you're really talking about a sealed unit, which means you're probably going to go liquid cooled, which also then you got to figure out how to do that from a high reliability. So remember, your systems engineer, the customer is probably thinking, hey, I want all this AI processing in my iPhone size box, and you're thinking, man, I need a trailer to tow this around. And the reality is, it's probably a shoebox type thing. So my point of all that is, be sure that you're thinking through all the trades. Can we if it's type 1 encryption, but can we do CFFC? That gets rid of some of the hardware. Can we relax some of the temperature because because we've got XYZ kind of constraints on a limitation? These are the trades that you, the integrator, supplier, and the customer need to think through. All right. So wrapping up here, and I'll hand it over to Matthew, but AI at the edge is a lot of things more than just raw computing power. So it's a combination of speed, security, and ruggedization, resilience in very, very harsh environments. And your job is to help balance those by having a decision-making framework in place with your customers, your suppliers, and with your team itself, so that you can design for fantastic speed, processing capacity to meet the hardware and software needs of the customers and be able to survive in those mill standard and other environments. With that, I'm going to hand it over to Matthew, who's going to talk about securing AI at the edge.
Thanks, Cale. I think that was a really nice introduction into some of the things you have to think about with your hardware needs. So I'm Matthew Fahrenkrug. I'm a senior embedded software engineer at Starlab. We're a small cybersecurity company, and we specialize in embedded security for a variety of sizes of things, but often you can think like unmonitored systems. Primary use cases is for data protection, anti-tamper. I've been here for 7 years, and my background is pretty low in the stack, right at that intersection of hardware and software. So low-level security, secure boot on systems, kernel protections, how to make systems immutable. Basically, everything needed to develop products that can protect systems from really the data center to the edge, and to make sure they're able to keep running. So we're all kind of aware of different ways that the edge, that autonomous platforms are kind of rapidly evolving. There's been different market pressures that are forcing changes. There's been a rise in demand for the idea of producing these cheaper and cheaper and much, much more quickly. We've had a rise in technologies that allow us to really have much more capable systems than you could even just a few years ago, but also much more complex systems. And all of this is driving, maybe some new concerns around the security of systems. So I'm gonna, so there's some political and social challenges here. We're seeing a lot of changes in the last few months. There's challenges around where our supply chains are, that they're being based in certain places, concerns about the ability to maybe import even things like chips that you really depend on. There's pressure around having more automation and digitalization so that you can speed up the development process and you can deliver something much more quickly and reduce your time to market. We're also entering this kind of period of acceleration into new technologies. So high performance compute and connectivity are available now at much lower price points and much smaller form factors. Like Kale was talking about, the idea of the swap C space that you have available, whether it's something the size of an iPhone or a shoebox or a trailer, we're increasingly seeing you can get that trailer size thing in a shoebox or that shoebox size thing in an iPhone, which means you have a lot more power to play with on your autonomous platform. And all of these kind of changes impact the security profile of your systems. You've probably heard people starting to talk about the need to secure the software development lifecycle. So not just thinking about supply chain in terms of all of your hardware components, but thinking about supply chain in terms of all your software components, making sure that every one of your software pieces is coming from the place you think it's coming from, that someone else hasn't modified it on the way. People are also talking about things like the SBOM, the software bill of materials. We're needing to meet different NIST requirements like 802.18, which are standards that exist to help reduce vulnerabilities in your software. So at Starlab, our goal is to move past just the observation of attacks and go to surviving them, which this idea we call cyber resiliency. There's also been a number of emerging security challenges as you bring in autonomy and AI. But from a security point of view, we use a lot of the same techniques for dealing with them. So there's an emphasis on data confidentiality. Within any kind of autonomous system, you're going to have particular data that's important to you that you want to prevent an attacker from being able to extract or modify. In a more AI sense, it could be a specific model or weights. It could be specific algorithms that are either proprietary to your company or restricted because of government sensitivities. You may have other sensitive data that's being fed into those or is being recorded from sensors on your device. And at the day, we've found for most of our customers, it's paramount that their data be protected at almost any cost. We also want to think about the ways that we measure output integrity with AI models. So there's always concerns about trusting that the data you put in to one of these models and the data that comes out are all the correct things. And there's ways that you can make use of guardrails to ensure that the outputs are correct. And finally, it's important that your system always be available whenever it's needed. So you've got something that's integrated a bunch of sensors onto a platform where there's not necessarily a human in the loop, and you need to know that it will be able to keep operating for as long as it needs to operate, and that a piece breaking or worse, an attacker trying to compromise your device doesn't stop it from being available. So you can see over on the right, we've got a list of the solutions and remediations, and I'm going to talk through those next. Here at Starlab, our mindset is that the attacker is already on your system. We're running, even on small embedded edge devices, kernels and operating systems that have millions of lines of code that have innumerable entry points. So our starting point is the idea that somewhere at some point, there's going to be a way that an attacker gets onto your system, and we want to mitigate that. And the way we do it is we start by designing for security. So if you know your system's going to be compromised, how can you minimize the effects of that altogether? We want to make sure that critical applications can still run and that threats can be mitigated when the attacker is there. We have 7 tenets that we use to guide our security development listed at the bottom. I'm going to speak to a few of these during the presentation, but if you want to hear more about all of them, I'm happy to have our company schedule a call with you to talk about them. One of the places you have to start is threat modeling, which is not the most fun place to start, but is very necessary. It's important to know exactly what the basis for the level of security that your system requires. So thinking about who's possible to attack, what kind of entry points you have into your system. Is it via network? Is it via someone managing to get hands-on? So you have to understand what your system is already doing, and then what level of security you already have on your system. And starting from that point, you can go forward and say, what do I need to do to secure it? We go through the idea of separating your functional and your non-functional requirements and seeing how the security impacts both of those. Overall, this kind of reveals how valuable it is to have an immutable system, because in an immutable system, an attacker is unable to impact huge swaths of things. If they can't, an attacker, maybe they want to extract data, but maybe they want to manipulate your sensor algorithms or pre-stored sensor data. But on an immutable system, they're not able to, which really limits the scope of what they can do. So data protection. This is really the basis of any security standard that you probably need to meet for your product. So at StarLab, we start with the idea of building a trusted computing base. So this begins when the device first turns on. They'll go through some kind of secure boot process, and that'll vary based on the type of processor it has, what sorts of hardware root of trust are available on it. But from the very beginning, each stage of code that runs validates and verifies the next one. And maybe you have something like a TPM on your device that is measuring the boot process to let you know if anything is happening that shouldn't be. But as you go through boot, you want to make sure that nothing has been tampered with, so that when your system is running, you know that you can trust it. So we go through the bootloader, we go through the kernel, and all the way up through to your system itself, the rootfs, and ensure the integrity of all of those components. We also want to consider the idea of how the device might be tampered with. So we're talking about physical systems that are deployed into an environment where that's likely unfriendly, that isn't going to have necessarily our people around it or other systems around it monitoring it. Someone might be able to put hands on it at any point. And so all of that really drives a necessity for protecting the data on the system. And the best way to prevent and to remediate tamper on the system is to always ensure the integrity of all of the software before it's allowed to run. So we start from a real secure boot solution to provide a root of trust that validates the integrity of all of the rest of the system. We're also going to focus on the idea of attack surface reduction. So like I said earlier, there are a lot of components on one of these modern systems. And we're going to, as you go through the whole development process, try to minimize the way that anything unnecessary can be used to attack the system itself. So this goes from during development, when we think very carefully about things like the software bill of materials that I mentioned before, about minimizing ways that the code, like the source code, can be attacked, that anyone could tamper with the development process. And then that feeds into build time when you want a system in place to ensure that as the software is built, it's signed and verified, and you know that only the correct source code is feeding into the correct binaries that are going to be run on the end device. And finally, during runtime, you want to have a solution in place, like I was talking about before, that starts with secure boot, but that then extends into something like allow listing. So allow listing is a technique for ensuring that only the correct code on a system can be run, that an attacker can't bring in anything else and be able to run it on the system. Only the programs that were deployed with the device can run. I referred a little bit earlier to the idea of immutable. So one of the ideas here is you have an immutable system as a whole, and then you're going to break that down to all of the individual components. So you want to divide your system up and have each isolated component itself be fixed and independent from each other, so that compromising one component doesn't make it easy to compromise another. Instead, every component on your system, and here I'm focused more on software, but you can see the hardware analog easily. So every software component you have should run individually, so that if someone was able to compromise one piece, they wouldn't be able to impact the rest of the system. This can go as far as looking like having virtualization on your system. So the idea that you add in an extra layer, a hypervisor, to help mediate the hardware resources on your system, to feed into applications so that only the application that needs access to networking, for example, has access to networking, and none of the other applications would have access to it. None of the other applications would be able either to reach out on a network if they were compromised, and it just limits the ability for them to be compromised if someone's not able to reach them over the network. So rather than having every sensor available to every running program, you want to divide your system so that only an algorithm or model or anything else that requires access actually has it. So we propose having a case for change. We are interested in building in security to a system, not bolting it on later. So starting from the beginning in that development process, like I said, making choices that will result in a more secure system, sometimes months or years or decades later, because we know how long these devices might keep on running for. Not only the idea of how do I prevent attacks, but how can I survive them? If one piece is broken or attacked, can the rest of the system continue fulfilling its role the way it should? How will the rest of the system operate when it is attacked? Because there are critical applications that need to be available. And there's a critical device on a system, and it needs to be protected, even if the attacker is resident on the system. So if you'd like more info on us, I have linked to a number of blogs that we've written, and you can go to our website to see them. We write kind of a range of stuff from very technical to very high level that cover some of the challenges of securing systems, preventing tamper, from our years of experience working in this space. So this is stuff like secure boot, application allow listing, all just kind of basic features on any given device. We've also got a number of great technical materials and white papers on our site for how to think about securing your systems. Thank you all very much, and I'm going to hand it back over to John for some Q&A.
Thank you, Matthew, and thank you, Cale. Excellent presentations. As Cale said at the beginning, I think these guys could go on and do an all-day session on this topic. But we don't have time for that, but we do have time for your questions. So let's get to the first one from the audience. This one is for Cale. Actually, Cale's not back on yet. We're going to get him back, but I'm going to start with Matthew then. Matthew, how can hardware-based security, e.g. TPM, secure enclaves, be integrated into edge AI systems to ensure data integrity and model protection?
Yeah, so these are hardware components, TPM, secure enclaves, that have to exist in your device. So a lot of them are coming on the chips you're using. But the idea is they help provide a hardware root of trust. They provide a starting point for secure boot on a system, and then that can be extended through the rest of the boot process into the operating system and help you validate and verify everything that you're running on the system itself. So you can depend on these hardware components to provide the actual validation that everything you're running is what you mean it to be, whether through keys or other methods.
Okay, I got a question here from Kale. What are the environmental limits for AI at the edge? Does AI have an environmental limit? Really good question. I mean, it makes you think philosophically.
Yeah, I'll stick to the engineering. I'm not sure. Yeah, there's probably a philosophical, existential type of question there. But honestly, it's there. The limits are going to be primarily around the ability to cool at the high end or the higher temperature. And the short answer is, yeah, yes, there's probably an operational limit, but it's really going to be constrained by how much cooling you can actually deploy. So you can have a whole lot of liquid cooling and get a very, very high operating temperature. The problem is that's probably going to violate your swap. So this goes back to the conversation of it's always a balance. You're trying to optimize and find that sweet spot of size, weight, and power, processing power, operating temperature, and other requirements. So that routinely we're seeing, and we're operating at certainly plus 55C. We have seen some and fielded some things at 60 and 65C. You start getting up to 75 and 80 and 90, and it just becomes a cooling problem. Because the thermal's got to go somewhere, and so that then actually elevates it to more of a on the platform, where can we move this heat and get it away from the box, and it's got to go somewhere that probably isn't 90C kind of thing. So there's your answer, which is probably more of a non-answer.
Works for me.
Okay.
I've got a question here that's not assigned, but I'm going to give it to Matthew. Doesn't adding virtualization to the kernel space increase the attack surface exactly where you want to minimize it?
Yeah, that's a good question. So when we talk about virtualization, people mean sometimes a little bit different things. So some of the technical words that get thrown around are the idea of like a type 1 versus a type 2 hypervisor. That has to do with more of kind of the levels of where they sit. So a type 2 hypervisor more often lives at the kernel level and is separating things there, whereas a type 1 hypervisor is going to sit below the kernel. And so on a system with a type 1 hypervisor, you are able to really hard limit all of the resources on your system to different virtual machines. And so that kernel on the virtual machine only has access to a portion of the system that it's on. And what it does is it actually reduces the attack surface if that kernel is compromised. And I could talk for another hour on the topic of securing virtualization, but I should let Kale answer some questions.
The next webinar will be on attack surfaces and virtualization. So we got that. I got one for Kale here. AI and the components it runs on are constantly evolving. How do you keep up with that evolution while also ensuring your tech is secure when deployed at the edge? Is that a back-end way of saying that commercial technology isn't always secure when you implement it?
Yeah, it could be. Yeah, I think the first part is exactly right. You've got the hardware baselines, the processors, motherboards, the memory, the standards that are associated with all those they're always adapting, and it's primarily driven by the need for speed, power optimization, cost optimization, and it's in response to a lot of market influences, primarily around just the big data farms and whatnot, and processing farms and whatnot. So first of all, the key thing is to accept that yes, it's going to change, and that means a couple of things. One, you need to plan for that change in your product line management. So you got to have a way, a process in your engineering and your manufacturing and your supply chain to ensure that you can figure out, okay, if we've got customers that need, a commitment to 10-year unchanged hardware, well, that's one thing, or 20 years or 30 years, like a lot of defense customers. Versus, hey, you've got maybe a commercial customer that can accommodate the change. So you got to make sure that your product line management from inception of the idea all the way to the factory, you've got the process to go deal with that change and make sure that aligns to what the market needs. The second thing to do is you got to really stay on top of the supply chain relationships and make sure that you've got those relationships, pull everything to the left that you can in terms of when are the new standards, what are the standards, influence the standards, influence the capability and the timelines, and then internally prepare for, all right, here are the changes to the design, the capabilities, what do you need on the factory floor, and everything in between. The last thing, and Matthew probably can speak to this as well, is you figure out how to best isolate the variability in the hardware from the variability in the software, and that gets into the magic of the hypervisors and that kind of thing, and trying to isolate some of the changes, but endeavoring to figure out how you can isolate the variability through, I'll say, middleware in big quotes because that's a very vague term, but anytime you can isolate that variability, and that requires a system level thinking. So that's your customer, your supply base, you, the integrator, that kind of thing, all thinking through, again, from a product line, from the bare metal up, how are you managing that variability?
Did you want to add anything, Matthew?
Yeah, I think Kale covered that pretty well at the end there. It's really it's an additional challenge we have in modern times with hardware complexity the way it is, and then trying to maintain with software that same idea of locking in for an extended period of time, 5 or 10 or 20 years, something with minimal changes that can keep running on the same hardware, or maybe on a couple revs of the same hardware without introducing new bugs or vulnerability. I think I would just say it adds a lot of challenges to the way you do testing and validation. I think that's where people see it the most often. But also a step before, when you design a system, there's things you can do that will make it much easier to iterate on in the future. And so I think we're finally getting to the point where there's interest from customers in thinking more proactively about that and investing some resources up front to make sure that you really can keep running the same thing for a decade without having a lot of maintenance and technical debt start biting you, 6 or 7 years in.
If I could glob onto that, John, Matthew's spot on. When you can start talking with your customers about, well, you want the latest and greatest capability because you got use case A, or you want whatever kind of capability. Immediately start talking about what is the tech refresh approach then, because their requirements are going to be evolving, and they're not going to be, I need less processing, I need less thermal, that kind of thing. It's always more everything. So you're exactly right, Matthew. The earlier you can start the conversation of whether it's planned tech refreshes, maybe I'm making numbers up here, on a 2-year, a 3-year, right, versus, hey, unchanged for 20 years. Those are two separate conversations. And as long as you can plan for it, then you can start driving that into, okay, what's the design to cost? What's the from a manufacturing standpoint, you're planning for that, the variability, the modularity. You're spot on, Matthew.
Thanks, guys. I think, what you touched on in the beginning of your first answer there, Kale, was, looking at where it comes from. It comes back to the whole trusted supply chain, which the DoD is pushing as well. That kind of factors all the way. It's not just at the end. It's not just at the software. It's like where you get everything from.
Quite right.
So that's a big part of it. So keep these questions coming. I got one more here. What about zero trust at the tactical edge, and to be able to support these tools at the edge? Who would like to answer that? Question 9 here.
Yeah, I can take a stab at it to start. So zero trust is super buzzwordy, right? We're seeing it all over the place the last few years. Means kind of a few different things depending on who you're talking to. I think where we see it really matter from kind of our approach of more secure by design is that you want to you're really chasing after having individual components that aren't reliant on trusting other components, especially unauthenticated components. Obviously, zero trust also gets used to describe different authentication mechanisms between two platforms, whether it's to someone's servers or to another device. It can add a lot of complexity in that case. I think I'm trying to remember the second half of that question.
To support the tools at the edge.
Yeah, and I think for supporting the tools at the edge, one of the things you're going to see is that you have to design this into your system from the beginning. Trying to refactor something into a zero trust secure by design years later is going to be really tricky and really expensive. So tooling wise, you want to design this in from the beginning or as early as you can in your actual development process. And then you're going to need to think about things ahead of time, like how am I going to update this in the field? That's a really hard question that a lot of people don't want to think about until it's already in the field. And at that point, it's like, well, you've kind of bought yourself into a corner. So if you start thinking about things like updating the field, what to do if a device is compromised, do you have a solution in place that deals with one device being compromised without it affecting your other devices? Things like key revocation. These are all things you can plan for and design for, but you have to do it up front.
Yeah, you don't want to just have to throw it on at the end as an afterthought. Next question. I think this one I'm going to throw over to Cale. From a hardware standpoint, what I/O is critical for UXV application? Are things like TPM, PoE, CAN important moving forward?
Yes. Yeah. Yeah. All of those things. In my experience, to be honest, it's everything, and it's everything in the sense of that. There's a subset for kind of each domain. So aerospace or airplanes, drones have kind of gravitated towards one set of standards. Ground vehicles generally gravitates towards different Ethernet or some type of Ethernet is pretty common, but then it varies whether it's copper or fiber, and then what kind of network and that kind of thing. I think you mentioned CAN bus, John. That gets into that's the standard in the vehicles. So they're using they're not doing a ground up vehicle design; they're adapting a vehicle. So the short answer is it depends on the air vehicle. And so I'd flip it around and say, or not the air vehicle, sorry, the vehicle itself. And so what you got to do is flip it around and say, well, we've got to be able to, we know we're going to have these in aerospace. We know we're going to have these in surface vehicles. We know we're going to have these in ground vehicles, subsurface, that kind of thing. So the intent, what we as integrators and designers have to do is figure out how can we modularize that I/O component so that your core, your processing GPU, memory, right, that kind of thing, and then not burden a ground vehicle with a bunch of mil standard 1553 that they're never going to need, right? But they do need the CAN bus. They absolutely need fiber, maybe probably more copper or anything like that. So the intent is isolate modularize the I/O, right? Abstract it from a hardware perspective, from the processing and whatnot. And then it's ruggedize the hell out of the connectors, right? And that kind of thing. So bring it out in a standard way that the factory can do it, cheap, fast, that kind of stuff. So again, I'd say it depends. Big ones, absolutely. Ethernet, 100%. Then after that, pick your favorite one. And I guarantee you there's another 10 behind it that everybody wants.
For a second, I thought you were going to say modular up, which reminded me I'm a Red Sox fan of Cowboy Up back, but I think that would be a good phrase for the most of the world. We got a modular up.
I like that.
Yeah. So I got a question here from Matthew. How can companies protect their AI models that have been deployed from potential tampering, intellectual property theft, or reverse engineering? Isn't that that's the gold $100 million question, right?
Yeah. And like all the answers in this space, it depends on how valuable it is, right? Or it depends on what your constraints are. I think there's a lot of very simple steps that you can take that get you a 90% solution. Things like having a secure boot solution in place to ensure that only your software is running on a device, that's table stakes now. If you're not doing a secure boot solution, I don't know what you're doing, but it's not security. There's basic things when you've got software running on the system, you want some kind of allow listing, or as it used to be called, like whitelisting approach. So something that ensures that only the executables that you authenticated ahead of time and deployed to the device are the thing that can run. It makes it much more difficult for an attacker to bring their own code onto your system, which makes it much more difficult for them to either tamper with the system or to extract things from the system. And then above all, like I said before, you have to start by designing security from the beginning. You can't just bolt on only solutions after the fact, but you need to really think through carefully how you're going to secure your system from the minute you begin designing it.
Okay. I got a question here for Kale. What are some hardware design considerations when implementing your Crystal Rugged's tech on autonomous platforms?
I think, to quote Matthew, it depends. It's really going to a couple of things. Again, if you kind of think thermal is going to be your big challenge, excuse me, thermal is going to be your big challenge, and then you're constrained probably with the size of the boards and the parts that you're integrating, kind of thing. The challenge is going to be how do you satisfy the expectation of a small form factor, which is going to drive the density and get the heat out. And so a lot of what goes into our design in terms of the ruggedizing it is going to be figuring out how do you design for structure and for thermal management. So don't have two different systems, meaning thermal management and structural. So it's literally the same system, because we just don't have the volume. We don't have the size, weight, and or power to go have two separate systems to manage those two separate things. So a lot of what we do is integrate thermal management and structure. So you use the structure to do the shock of the vibe, but you also use it to help move the heat away from the devices to the parts of the box where you can actually then have it pull it away from the actual box and dissipate it, make it somebody else's problem at that point. So a lot of that is around like machining to, sandwiching boards in between metals and where you're trying to basically create cold plates that are also, again, structural. There's pros and cons with that. You do end up there are weight implications, but again, this is the trade space of, if you want to cool, you're going to have mass to pull the thermal away. That also is how you get your shock and vibe isolation. So a lot of it is around, again, figuring out how you optimize the systems and combine the systems for thermal management and structural.
There's another question here that kind of follows up on that. Is what are the techniques that you use for ruggedizing COTS technologies? I mean, I guess taking commercial stuff and making it live in a military environment, right?
Sure. I mentioned I already covered a couple there around machining for thermal and vibe in terms of the chassis and whatnot. Another couple other techniques is there's definitely a lot of coatings you have to apply to the boards to ensure that you can do, whether it's conformal coating or otherwise, to ensure that you prevent as much as you can the dust fog, salt fog, that kind of thing. Other things we do around use a lot of connectors, a lot of high-end connectors, and I chuckle because they're big and they're bulky, but they're the way that you can isolate the hardware, from the outside world, try to isolate some of that variability. And then other things that we do is there's a lot of, especially anytime you have a connector, you generally have a risk of vibration, and which means signal integrity issues and that kind of thing. So there's a lot of techniques around using adhesives and high structural with adhesives to ensure that where you do have those connection points, electrical, mechanical, and otherwise, that you don't have any kind of frequencies that drive them to vibrate and therefore cause friction, disconnects, reducing the reliability and that kind of thing. So it's a question of structural, mechanical, a lot of electrical connections, a lot of adhesives, a lot of coatings and whatnot. And then lastly, I'll say a lot of it is around designing the box to try to vector or channel the thermal out. Again, I know I keep talking about thermal, but if Matthew's going to talk a lot about security, I'm going to talk about the heat from it. And a lot of it is arranging the system so that you can actually extract the thermal. The last thing, but to wrap it up though, I'll say so much of this is, yeah, you can simulate and you can use good engineering practice, but ultimately the best thing to do is to put together a design and go into your your in-house compliance lab and evaluate it, test it, instrument it, and figure out what works and what doesn't. Sometimes that's much faster than sitting around at a computer trying to simulate very complex and sometimes unknown kind of geometry.
Okay, I got time for one more question. I'm going to give this one to Matthew. Is how can organizations effectively balance their security needs of autonomous systems with the performance requirements of real-time processing?
Yeah, so like Kale has touched on a few times, we all like to have the system with 64 2.5 gigahertz cores and all of the NVMe, but we don't always have access to that, whether it's for thermal reasons or power reasons or space reasons. We live in constrained worlds. So if you've got, a system that is trying to do a lot, is probably already near the limits of what it can do already, you don't want security to add this huge overhead that stops the system from doing what it needs to do, right? Yep. At the end of the day, the system has a job that it has to do, and if the security solutions or mitigations you're putting in prevent that, that's a failed solution. The same as if a sensor failed or anything else. So the way we think about it is there's a lot of things you can do with using lighter weight encryption protocols, with using hardware acceleration, AES acceleration for a lot of different things, trying to rely very carefully on validating things early rather than continuously. And honestly, the biggest thing is upfront. When you've designed your system and thought through security, you do your risk assessment then, and you make sure you only add in the security controls and limits that you actually need. For a system that's being deployed somewhere locally or under physical control, you need very different security than versus something that's being deployed autonomously somewhere else where maybe someone we don't want can lay hands on it. Those are two very different scenarios, and so you need to apply two very different sets of security controls to them.
Thank you, gentlemen. Before we wrap up, you want to give a shout out to your websites and where people can learn more?
Sure enough, Crystal Group, you can find us at crystalrugged.com. And if you'd like to reach out, you can hit me up at kale.stevens@crystalrugged.com.
Yep, and our website is at starlab.io.
Excellent. And that brings us to our time limit for today. Sorry we did not get to all of your questions. Someone may get back to you after the event with more information. I want to thank Kale and Matthew for excellent presentations today, and Crystal Group and Star Lab for sponsoring this session. This and all Open Systems Media virtual events are copyrighted and may not be recorded or used in any way without the express written consent of Open Systems Media. This event will be archived online today at the same URL you used to join today's live session, as well as the URL shown on your screen, and be available for at least 1 year. Now, please be sure to attend our next session, Navigating Safety Certification and UAS Platforms, where I will be starting that session at 2:15 p.m. Eastern Time. Thank you all.
Hey, guys.